All right, recording is rolling. It's Tuesday, November 14th. Our main focus today is going to be these Chapter 9 puzzles. Now, we've done about half of them so far. We're going to knock out the other half today. Just turn in your work for these puzzles sometime before you leave for Thanksgiving break. Yeah, so got a little checklist here, things to check, make sure. Probably class, good idea. Check, focus, make sure you got everything in going into the break. Right. So your energy quizzes, I put back in your folders. You may pick those up already. If you want to do corrections, just make sure you turn corrections before the break. Momentum half page. I'm talking about this one right here. Now we did all these questions in class together. So as long as you followed along, probably always right. A lot of you guys already turned this in. If you haven't, just make sure you turn it in before Thanksgiving break. That'll be in the grade book. The interim period actually ends tomorrow. Tomorrow's the last day of a certain interim period. Teachers have a while to put grades in. So I think the last grade that's going to go in is tomorrow. I'll give you guys a bounce ball lab. You say like, how bouncy is bounce ball? Physics term is coefficient of restitution. So for tomorrow, right? And then this Friday quiz, which is going to be energy and momentum. I'll just put that like post interim, right? But that'll be a Friday quiz, right? I'm sure there's going to be some students absent on Friday that have to make this up after the break, so that'll probably be a thing too. Right? We'll do a review on Thursday of both energy and momentum. I won't give you guys a take-home quiz for momentum. We'll just put it all on just in class quiz on Friday, right? But that'll cover for 2 sessions, right? So energy and momentum. All right, so you guys good with what's going on in this class? Good. All right, so let's hit these chapter 9 puzzles. Chapter 9 puzzles. So the last one we did, I think, was number 70 with the rockets. I think we finished that, right? Here, guys. Everybody focus here? Here? All right, guys, write these down. Should be easy points. Just follow along. All right. I think we finished number 70 rockets, right? So number 77. A so many gram rubber bullet travels with the velocity so many meters per second. Oh, it strikes a stationary so many kilogram concrete block. Right? And ricochets in the opposite direction, but boing with some velocity, right? And look, they were really nice. They even told you it was a negative velocity, right? Which, of course, is the only way it could play out. But sometimes textbook questions are a little sneaky with directions, right? How fast will the concrete block be moving? Ooh, right. So a few things before we go like plugging and chugging. Like I definitely see some collision. So this definitely be something to do with momentum or impulse, right? If you just got a physics question out of the blue and you didn't know like what chapter is this from? Okay, what's got to be momentum impulse because some kind of collision, right? Notice, did you guys catch that the masses of the bullet versus the block? Look at those units, grams versus kilograms, right? So eventually when you plug numbers in the calculator, can you just use the face value numbers that are exactly given to you? No, right? You got to make sure that they're consistent units. Maybe I'll go all kilograms just to be, that's normally a safe thing to do, put them all in kilograms. And if you do that, that's how do you go from grams to kilograms? Divide by 1,000. Yeah, over 1,000, right? Right. Interesting, they gave you the ricochet velocity and scientific notation. Your book likes to do that a bit, right? Guys, 10 to the 2. What's another word for 10 to the 2? 100. So you got negative 100 meters per second. Right. Another thing I want to think about before we start plugging numbers. Let's do a conceptual question. What if the bullet stuck in the concrete block versus boing, ricochets off like they gave it to you, right? Which concrete block? Here, guys, focus here. Right. Which concrete block would be sliding faster? The one where the bullet sticks, the one where the bullet boing bounces off. How many guys say one where it bounces off would be going faster? Bounces off. Yeah, right. The question, a version of that question came up a few times yesterday, and I think once or twice last week too. Okay. All right. So with all those considerations, let's see what we're going to do with this. Right. I'm thinking bounce. Maybe something to do with the momentum is going to be conserved between the bullet and the block collectively. So let me do sum of momentum initial equals sum of momentum final. So it's pre-collision and post-collision. Well, if the concrete block started at rest, I think all the momentum is provided by the bullet. Right? So could you guys say mass of the bullet times the firing speed of the bullet, right, is supplying all the momentum? Right? That's going to go to, right? Well, post-collision, I got like two different things going on, right? Got the bullet doing its own thing. Right? I'll call it V, well, V bullet final. How about that? Right? Plus the mass of the block going its post-collision velocity, V block, right? So that's the setup. Now we should know everything except for one thing. They said, oh, how fast will the concrete block move? Okay, so I think we're solving for this. Did they give you everything else? Yeah, they did give you everything else. Right? Maybe I'll change the numbers a little bit just to keep you guys on your toes, give you guys another example. Right? Maybe I'll get an 11-gram bullet. Right? So that's 11 over 1,000 kilograms. Right? They said fired at 150 meters per second. Maybe I'll make mine, about 180 meters per second. Let's change that a little bit. Right? And then, mass of the bullet shows up here again. So just copy paste the mass of the bullet. So 70 kilogram. Okay. Velocity of the bullet final. Now this is a negative number. So I'll keep a negative number, make up something a little bit different than theirs. So careful about what yours is going to be. Okay. Right. And then plus mass of the bullet, or is it block? Right. Maybe I have this many kilogram block. Yeah, something a little bit different from the bullet. Velocity of the block. Okay. So my numbers are a little bit different. They're not crazy different. Just different enough. All right. I'll get started. So you can see the process here. All right, so I'm going to take this term, I'm going to add it over and divide by the mass of the block. Right? So a couple algebra steps later, getting V block is, right, let's see, bullet mass, bullet mass, kilogram, times firing speed of the bullet, meter per second. Right? Now, minus and negative. Right, and then that's all collectively divided by mass of the block. Right, just like that. Right. You know what, too? Let's think about this. You see how the block is approximately 1,000 times the mass of the bullet? Not exactly, right? But roughly, it's the same magnitude, right? It's roughly 1,000 times, right? Almost. Right? The bullet changes its velocity. It looks like pretty elastic, maybe not perfectly elastic, but closer to that end, right? So the change of velocity of the bullet is, well, it's like the initial speed times 2, kind of, right? Because boing rebounds, right? So I'm thinking that the transfer of momentum is going to be kind of like, mass times velocity. I'm trying to come up with an estimate before I start plugging numbers into the calculator. Make sure they get something at the end that looks reasonable. I think, let's see, over 1,000 times 1,000. Right. Maybe if I take the speed, divide by 1,000, it'd be like 0.2 meters per second, and then kind of times 2-ish, like 0.4 over. Okay. I'm gonna guess 0.4 meters per second. I think this block is going to be going approximately 0.4 meters per second. Maybe plus or minus a little bit. That might not be exactly the answer. Right. But if we get something pretty close to that, then I can say I probably did this right. So I'm going to guess 0.4 meters per second. Velocity block is, right, so I got 11 on 1,000 times 180, right? Ooh, minus a negative. Guys, can I just go plus, just like that? Okay. So plus 1,000 times 20, all collectively divided by mass of the block, right, is, hey, look at that, 0.44 meter per second. I just made up some numbers on the fly. I didn't know what the answer was going to be. I was guessing about 0.4 meters per second. Yeah, it came out pretty dang close to that. Right? In physics, it's a good idea whenever you get an answer, check, make sure at the end, like, does that look reasonable, right? And well, no, it does, because little math bonus there, right? Another thing good to check for collisions. Suppose you just make up a bunch of collision data, right? A good thing to check is kinetic energy before and after. Make sure that the kinetic energy did not increase. I'm going to run a check real fast. I'm going to run a check. Let me do maybe this margin right here. What is K initial? What is K final? Like pre and post collision, right? So 1/2 times mass of the bullet times the initial speed being squared, right? Looking like 178 joules, right? Now post collision, I got two different objects on the move, right? The bullet and the block, right? So 1/2 times bullet, oops. I do that too, yeah, we're good. Clear. 1/2 bullet mass times the post collision velocity squared plus the block. So 1/2 mass blocks times this post collision velocity, which is this tiny number here, squared, right? And I'm getting, 79.9. Let's just call that 80, yes, like joules, right? Yeah, do you guys see how the kinetic energy decreased? Right? So that's okay. That's what you would expect during a collision. The kinetic energy to go down. If it was the same value, you could call that perfectly elastic, right? And then, yeah, so this is less than that, which just makes sense. All right, you guys good with the bullet and the block? Right, number 78, skateboarding. Got Kofi, has a mass of so many kilograms, riding a skateboard with this mass, traveling at so many meters per second. Kofi jumps off the skateboard and stops dead in his tracks. What direction and what velocity did he jump? All right, so number 78. Draw this out. I got Kofi on a skateboard. So I got massive Kofi. Here's massive the skateboard. Okay. And they were initially traveling together at some initial velocity. Okay. All right, so this is all like pre jump, right? And then at some point, Kofi's gonna jump. And it's gonna send the skateboard flying, I guess, to the right. So that, let's go on some wheels on saying it's not quite a hoverboard, right? Right. So now the skateboard's really flying really fast, right? I call it velocity skateboard, right? So that Kofi comes to rest and then comes to stop, right? And now that's at rest relative to what? One of the first things I told you way back in the day is that all velocities are relative, right? We got Kofi, we got the skateboard, and maybe the relative to like the ground, or I'm going to draw a tree in the background, like relative to this nearby tree, Kofi comes to a dead stop, right? You know what this problem reminds me a lot of is on this half page that we did like last week. You guys remember there was a problem like you throw a grenade and explodes into two parts, right? Hey, that's kind of like there was one giant mass and pow, like post jump, right? Like post explosion, post jump, right? You got two different masses going on, right? And the way we solved that is we said it's kind of like an inelastic collision, but in reverse. Like if you film this whole thing, like the grenade in reverse, all the parts coming together make one giant grenade, right? Here, if you film Kofi jumping off a skateboard and then run that film in reverse, it looks like Kofi jumping on the skateboard and it makes one giant mass. Okay? So we're going to treat this like a reverse collision. I'll say momentum is conserved. Sum of momentum before the jump equals sum of momentum after the jump. Right? Now, also a lot like the grenade, I'm going to say if I kept an eye on kinetic energy, I bet the kinetic energy would actually go up in this case. And it's coming from his muscles. Right? He's pushing, right? It's adding energy to the system, right? But we're just going to focus on the momentum, right? To figure out what is the well, here, let's fix that. So momentum before the collision, well, it was Kofi plus the skateboard, so that combined mass, right, moving at the initial velocity, right? And then after the jump, well, we got two separate things going on. We got Kofi at final jump for Kofi, right? Plus mass of the skateboard times velocity of the skateboard, right? But you know what? Part of the premise was that Kofi comes to a dead stop relative to like this nearby tree or anything else, right? So what is the final velocity of Kofi? 0. So let's just call it 0, just get rid of that term, right? So it's like all the combined momentum just all went into the skateboard. Right? Well, I bet that skateboard's flying real fast now. I'm gonna plug in some values. I'll put some numbers that are a little bit different from the books, change things up a little bit. They gave Kofi as so many kilograms. I'm gonna change the mass of Kofi. Let's make it this many kilograms, about that. Right? And I'll give him a this many kilogram skateboard. And I'll say he was going at, how about this fast, meters per second. It's a little bit different, a little bit different, a little bit different. Okay. Okay. And then, well, all of that momentum is all going to go into the skateboard post jump. So copy paste the mass, the skateboard, and then velocity skateboard. Right. Now the question they asked is how fast did Kofi jump? It looks like the setup what we're actually solving for is how fast is the skateboard moving after the jump. Right. So let's get that number first and then think about what from there. looks like very simply algebraically, all I have to do is divide down by the mass of the skateboard, right? Divide by 3 kilograms. Right? So it's 45 plus 3, all times the initial speed, and then divide by mass of skateboard. Right? Getting velocity skateboard post jump is this many meter per second. By the way, it's a really crazy fast velocity, but whatever, just run the numbers. Okay. All right, so the actual question is, how fast did Kofi jump? Right now, here's where I had different thoughts earlier. I'm just gonna stop there. I'm gonna treat this as the answer, but why would this be an answer, right? And what I was thinking earlier was things about like relative velocities. Like for example, let's think way back a few weeks ago. What if you're on a boat and the boat's moving through the water relative to the bank, like relative to the street, and you walking back and forth on the boat, right? Well, how fast are you walking? Well, relative to the boat is different than relative to like the tree on the land, right? You have to like add or subtract, right? You have different velocity vectors going on, right? I think I was overcomplicating this problem earlier. I think this would also represent how fast Kofi had to jump, because from Kofi's point of view, if he pushes exactly this fast, then his speed relative to the skateboard, right? Well, his initial velocity relative to the skateboard was 0. He was on the skateboard. Okay? Now he pushes this fast, which sends the skateboard going that fast relative to him because he's at rest relative to the tree. So I think this also happens to answer the question, right? Yeah, we're gonna go with that. Right. Right. Okay, number 79. Billiards. A cue ball with mass 0.16 kilograms rolls at so many meters per second, and bam, hits a stationary 8 ball of similar mass. Right. I think these balls might be slightly different masses. They say similar mass, so we're gonna mathematically treat that as the same mass. Right. The cue ball, baboing, goes at 45 degrees above its original path, and the 8 ball, baboing, 45 degrees below the horizontal. Okay. What is the velocity of each ball after the collision? Right. I have a whole poster just for this question, right. And it looks like this. Interestingly, AP in their college physics, they have a question that involves like a shuffleboard that also looks like the exact same picture, right? So billiards from your book, or shuffleboard from college physics, or right, it looks a lot like this poster. Okay? And the principle to solve this for a 2-dimensional collision, right? Collision happening in a 2-dimensional plane here, okay, is that momentum is conserved in each direction, like along each axis, x-axis and y-axis, right? So for billiards for you guys, there was a cue ball coming along that was providing all the momentum in the system, and all that momentum was in the x direction, right? So after the collision, bam, right? I could say that if I split those momentum values for each individual ball into components, say, well, how much to the right and how much up, and how much to the right and how much down, right? Cue ball, 8 ball, right? Then if I add up the momentums in the x direction, post collision, it has to match the pre-collision momentum provided by the cue ball. And then what about the y direction? Well, I could say however much this one's going up, mass times velocity, right? This component of that upward has to match this one downward because it has to zero out, right? This up and this down has to zero out because there was never any momentum in the y direction to start with, right? Right, so that's the framework I'm going to use to solve this. Let's try that out. I want to redraw that picture, number 79. Let's redraw that picture, right? And then so we can draw all the components and all that, right? Let me just use this paper to draw the picture, and I'll take out another piece of paper to do the math. Right? Right, so here comes the cue ball. Right? It's got some mass and some initial velocity. Let's call it V naught. Right? Right? They gave you both those values. Right? Here's the 8 ball. Right? Then bam! Right? Here's the collision, and it sends off the cue ball 45 degrees that way, and the 8 ball 45 degrees that way. Right? So 45 degrees. 45 degrees, right? Now, those are vectors. Those are momentum vectors, right? Mass times velocity, right? Which I don't draw very often, right? You guys see velocity vectors, you guys see force vectors, right? These are neither of those. These are momentum vectors. Right? I'm going to split these into components. Components, right? So the cue ball is now going to the right and up, right? How much to the right? How much up? And the 8 ball is going to the right and down. How much to the right? How much down? Is the momentum for each one. Okay. So let's call this mass times final velocity for the cue ball. I got mass times final velocity for the 8 ball. Okay. Now I maybe you can kind of see by symmetry that these are going to be equal speeds because it's equal mass balls. Okay. And how can you prove that? You can prove that with the momentum is conserved in the y direction, this x-axis, y-axis. Okay. So let's figure out these components. I got 1, 2, 3, 4 components. Okay. So here, gonna sort of cheat a little bit. I'm gonna assume these are the same velocity, but I'll say like even if they weren't, we'll show very quickly that they have to be the same velocity. Okay. So this is mass of the cue ball, and since they said similar masses, I'll just call it all m for some mass. Okay. So mass of the cue ball m times velocity of the cue ball post collision times what? Sine of 45 degrees would be that. Okay. And then down here, this would be mass of the 8 ball, which is, we're just gonna call it the same mass, times the post collision velocity of the 8 ball times sine of 45 degrees. Okay. And this would be negative because it's down. Okay. And then what about the side components? Let's fill this in while we're getting components. So this would be mv final cosine 45 degrees. And this would be mv final cosine 45 degrees. Okay. Okay. Now, what we haven't technically proven, that we kind of jump ahead a little bit, right, is that these v finals actually are the same. Right? If I label them differently, call this like Q and call this 8 ball, right? Then what I would say is that this minus this has to zero out. So let's go ahead and do that right now. Okay. I can list them as the same thing because it's going to come out to the same thing. Kind of getting ahead of what I've actually proved. Okay. If I set up sum of momentum in the y direction before is equal to sum of momentum in the y direction after collision, well, this has to zero out, 0 kilogram meter per second, because the cue ball was initially only traveling horizontally. Okay. So that's mv final, I'll call this q at sine 45 degrees, okay. And then minus, because up versus down, so minus mass of the 8 ball, v final 8 ball sine 45 degrees, right? Okay. But if you didn't see it before, you probably see it come together now, right? If these are equal masses, it goes away, sine 45 degrees, right? And I can very quickly say v final cue ball equals v final 8 ball. Right. Okay, so it's the same v final, right? So maybe it's a little overkill, but okay, you have to show it. Right? So same v final. Okay, so that aside, now let's go to the actual interesting part, which is what's going on in the x direction, because that's like where all the fun is, right? So sum of momentum in the x direction initial equals sum of momentum in the x direction final. Okay. And that was mass of the cue ball times the strike speed of the cue ball. Right? That's going to go into, okay, well, 2 rightward components for the momentum. Okay? So I got mass of the cue ball times velocity final. Now, since we proved that it's the same velocity final, let's call it VF at this point, right? Times cosine of 45 degrees, right? Plus, and then for the 8 ball, mass of the 8 ball, V final times also cosine 45 degrees. Right? Now it's different 45 degree angles. It's this 45 degrees versus that 45 degrees. But since it's numerically the same, then by the time we get to the math, it's all a match. Okay, so you guys get up to that point? Right. Got momentum conserved, the x direction, blah, 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 blah. Okay. I have 3 terms. Hey, do all those 3 terms have the m in them? Right. Right. They did give you a value. You could have plugged it in. But the important thing is that it's all the same mass. Therefore, it doesn't matter the magnitude of that mass, as long as it's all the same, right? If they give you 3 equal size marbles or 3 equal size bowling balls, then all the mass should also play out the same afterwards. Right? You get the same answer at the end, as long as they're all the same. Right? Who knows? What is cosine of 45 degrees? 0.7. Square root 2 over 2, or 0.707 if you said that. Yeah, this is root 2 over 2. Or 0.707 if you like. Yeah. So I like root 2 over 2. I'm going to use that. Okay. Same thing over here. This is root 2 over 2. Okay. Well, if we got root 2 over 2 of something plus root 2 over 2 of something, right? Half and half make a whole, right? So initial velocity equals final velocity times, okay, root 2 over 2 times 2 is just the root 2. That'll be like that. right? Because I'm adding two things together, right? And the question was, what's the final velocity? Oh man, we just solved this whole thing in terms of variables, didn't we? Yeah, pretty much. Right, let's just last step then. Final velocity is initial velocity divided by the root 2. Okay. They told you the strike speed was so many meters per second, so all you have to do is plug it in. Maybe for funsies, I'll change up the strike speed. I'll call the strike speed 5 meters per second. Right. So what's the post-collision speed of each ball? To be the strike speed divided by the root 2. Right. So for me, I'm getting this many. I'm going to save an extra digit here. Meter per second. Okay. Which is slower than the strike speed, but it makes sense it has to be slower than the strike speed because now there's two balls on the move. Right? Now they actually asked what's the post-collision velocity of each ball. So to turn this from a speed to a velocity, just include the directions. Say this is 45 degrees, like off axis for each ball, right? One up and one down off axis. Right? So include the angle. Right? There's one last check I want to do, and I'm going to do it in the space right over here. Save some paper. Right? I want to do a kinetic energy check because I know for perfectly elastic, kinetic energy would stay the same before and after the collision. And for any other kind of collision, it should decrease. Right? So what is the kinetic energy before? And what is, well, maybe we should say the sum of kinetic energy, sum of kinetic energy, like final, like post-collision for each individual ball, add them up. Right? Let's see, I wonder what kind of collision this was. So let's do my 1/2 times 0.16 kilograms times initial speed being squared. I'm doing my numbers, right? Oh, okay. I was not expecting that. I just made up numbers on the fly. I wasn't expecting that. That's exactly 2? Huh. All right, well, I guess it is. All right. So, all right, so 2 joules exactly I'm getting for my crazy made up numbers. Right? Then what about final? Well, I got 1/2 times 0.16 kilogram times this crazy number. It's rounded a little bit, squared. Right. And then another ball is doing exactly the same thing. So basically times 2, right? Right. Let's see what I get out of this. I'm getting, also 2 joules exactly. Right. Guys, the fact that kinetic energy happens to be conserved for this type of collision tells you it's a what type of collision? Perfectly elastic, right? A lot like this going on right here, except this is all in one dimension versus the billiards is, right? But extremely bouncy. Hey, I can believe that for billiard balls. Billiard balls are really bouncy, aren't they? And the same, perfectly elastic. Right? Now, interestingly, the numbers they gave you from the outset would only be consistent with what happened to turn out to be perfectly elastic collision. Right? Only perfectly elastic collision would they both take off at 45-degree angles. Right? All right, number 86. Oh, ice hockey. A so many kilogram hockey puck moving at so many meters per second strikes a so many kilogram jacket that is thrown onto the ice by the fan of a certain hockey team. I kind of wonder if there's like some history story that goes into this, but I don't know. I feel like that's a reference to something. The puck and jacket slide off together, find their velocity. Ooh. See, we're on ice. We got this, what looks like an inelastic collision. One thing's running into another thing. You know what this reminds me a lot of? Do you guys remember yesterday? Jocko on the ice? Right? You guys remember Jocko on the Whenever you open up a physics textbook and you're on ice, we're getting rid of the friction. Right? Jocko's catching the ball. Hey, just replace the ball with a puck and replace Jocko with a jacket. And you have basically the same question. Right? Now, earlier today, I was also looking at the numbers, and interestingly, there's also, maybe just coincidentally, similarity with the ratio of the masses. Do you guys see how? Here, guys, everybody look up here. You guys got cell phones away? Guys, look up here. Do you guys remember yesterday how the mass of the ball was a quarter of the total mass? Because 20/80 is like a quarter of the total mass, right? And therefore, the way the numbers worked out is that Jocko's speed post catch was like a quarter of the thrown speed of the ball. That's how the ratios worked out, right? It's like 2.5 kilometers an hour, right? Right. Well, if you look at the numbers given with the puck and the jacket, that's a really similar story, right? Do you guys see how the hockey puck is approximately a third of the mass of the jacket? Therefore, it's approximately a quarter of the total mass. Hey, How many of you guys think that the post-collision speed of the two moving together, sliding across the ice, is also going to be approximately a quarter of the strike speed of the puck, right? Because we're just like Jocko with the same ratios, blah, 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 right? A quarter of that's about 9 meters per second. I haven't worked out exactly with your numbers, but I bet it's pretty close to 9 meters per second, right? I'm going to solve this, of course, in front of you guys, and I'll change the numbers a little bit, but not a whole lot. I'll use the same hockey puck mass. It's probably some regulation number. Okay, so hockey. Let's get a puck going right here. Oops, let's make a 3D puck. Okay. Here's some curvature. All right, tell us mass of the puck. It's going velocity puck. It's going to strike this jacket of a certain hockey team. Call it mass jacket. And then, bam, they collide. We'll call it perfectly inelastic, and they'll slide together at some, I'll call it V final. Right? So collision, inelastic. Let's set up conservation of momentum. Sum of momentum before the collision equals sum of momentum after the collision. Okay? And it was all provided by the puck. So mass puck, this is, yeah, I guess not drawn to scale size-wise. Mass puck, velocity puck is providing all the momentum. Okay? That's going to go into, oh, well, the jacket plus puck, because that's one giant system now, one giant mass, right? Moving at velocity, final velocity, right? We're solving for that, right? So pretty plug and chug at this point, right? Remind you guys, where's my poster on this one? Here it is, here it is. Right? Looks a lot like this, perfectly inelastic. Right? Actually, even a step simpler than that, because the object B, the jacket in this case, starts at rest. You can get rid of that. Even simpler. Just bump this term. Boink. Right. So what you did. Okay. Let's plug some numbers. Mass of puck. I'll use the 0.115 kilogram. Let's say I'm going to strike my puck at 25 meter per second. Right. And then I'll have a jacket with mass about 0.4 kilogram plus the puck. Be final. Right. But you guys see how to finish this off. All you do is divide by the combined mass. That's it. Initial momentum divided by the combined mass. So here's the initial momentum, mass times velocity, then divide by the combined mass. Okay. So with my numbers I just made up, I'm getting like this many meter per second. There you go. All right. And you guys, with your textbook numbers, get something a little bit different, but probably not crazy different. All right, guys, good so far? Feeling readier for this quiz on Friday? Yeah. Got one more practice from this one. And of course, you guys got many that I did not circle. So if you want even more practice, then that's got those too. And number 80. A so many kilogram van runs into the back of a smaller compact car. They move together at so many meter per second. Assuming friction is negligible, calculate the initial speed of the van. Or how I might interpret this as maybe this post-collision speed could be, well, exactly that, like a post-collision speed. Even if there is friction, it could escape to stop. Maybe a more realistic version of this, rather than getting rid of friction, would be like, suppose you're a forensic investigator one day, and you come upon this car collision. Okay, well, I can pretty quickly get the mass of each car, so that's not too hard to get. Maybe each driver is seeing something different happen, right? So one guy says, the other goes, no, right? So they have an argument, right? And you as the investigator have to figure out what actually happened, what led to this happening in the first place. Oh, that's what speed mass right here. What was the initial speed of blah, blah, right? Right? So you look at the tread marks on the road and say, okay, here's the skid marks. So I can kind of back calculate how fast the post-collision would have led to the skidding happening. Right? And I know the masses. Therefore, right? And then you step back in time and blah, 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 right? Then you do a calculation like we're about to do right here. Figure out what actually happened with physics. Number 80. Right? So we got a big old van. How that mass van moving at velocity van. Right? It's going to run into this little turtle car, mass car. Bam. Right? And then inelastic collision. So they're going to move off together. So collision, right? Use the investigator, you pull up this formula and say, well, I know there was a collision. This would be one step of a larger process that you figure out, right? Got a collision going on, right? And the car was at rest, so all the momentum was provided by the van. So that'd be mass van, velocity van. Okay. And went into mass van plus car, or combined mass, due to its own post-collision velocity. Okay. Hey, that's kind of what we just did with the puck and the jacket, or Jocko catching the ball. Right? It looks all identical setup. Right? A little bit difference here, a little bit twist on this one, is we're saying, well, what led up to this in the first place? What we're actually solving for is that, okay, given that we figured out post-collision, how fast something about skid marks in the road. Right. So let's pop in some numbers here. I'll make up my own numbers a little bit different. Suppose I have a right. Suppose my van is like this many kilogram. Right. And how fast is it moving? Well, got to figure that out. Velocity van. Right. And then here's velocity, mass of the van again. Maybe have a this many kilogram car. Right. And then it told you how fast they slide together. Make up something, maybe like this many meter per second. Make up something a little bit different. Okay. Right. So what velocity van would have led to all that? Right. Oh, well, looks like algebraically just divide down the mass of the van. That's it. Divide down 2,000 kilogram. So let's go. This looks like 3,000 kilogram right there times somewhere per second, right? And then divide by the mass of the van. Right. I'm looking at the initial velocity of the van was this many meter per second. So that's how fast the van was going. Right. And if we got these two drivers with two different stories about what happened, say, well, here's what the numbers say. So I know the answer. Okay. Okay. Guys, good there? Another thing I want to check on this is, let's put something to test, because I just made up some numbers from scratch on the fly here. You guys tell me, what happened to the kinetic energy during this collision? Did it go up, go down, or stay the same? Kinetic energy. Yeah, went down, right? How'd it go down? Right? I forget exactly what's on the quiz on Friday, but that could be a good quiz question on Friday, right? Conceptually, what happens to kinetic energy? Let's see. What is kinetic energy initial? What is kinetic energy final? Let's see. Kinetic energy initial. So it was all in the van. 1/2 times mass of the van times initial speed of this van, which we found here, squared. Right, I'm getting that 126,000 some joules. Right. Now, post collision, got 1/2 times the combined mass times the post collision velocity squared. Right. I'm getting, ooh, yeah, 84,000 some joules. Yeah, the kinetic energy definitely decreased by a good amount. Right? Yeah, had to, right? That's a guaranteed. All right, so you guys good with those questions? All right. If you guys want to hold on to this for a few more days so you can use it to study, then go ahead. Anytime you want to turn it in, it's okay too. Make sure you turn this in before you take off for the break, though. Before you take off for the break. And put it in grades over the break. For that. All right, one last question today. One last question. Okay. There was a question I threw at you guys a few days ago we never actually solved. And that's called Magic School Bus. You guys remember Magic School Bus? All those kids on that frictionless field? Okay. So let's go back to that question. Right, there's like there's a mound here. There is a home plate over here. Right. And here's mass pitcher and the mass of a baseball. Mass pitcher, mass ball. Subscripts. And this ball was thrown at some speed, so I'll call that velocity of the ball. Right. And then because there was no friction, the pitcher went sliding off the opposite way. I'll call that velocity pitcher. Right. And the question was, well, how fast does she slide back towards second base? I said you can solve that using this conservation momentum stuff we're doing. If you only know their masses and the pitching speed, that's it. That's all you know. Right. But let's say the speed is going towards home plate, right? You know, it's a side thought here, since we got a couple spare minutes we can work with, right? How would the ball go a tiny bit faster Would the ball go a tiny bit faster if she's grounded into the ground with friction, or if she slides back the opposite way with no friction? The batter, where's the batter face a faster pitch? How about if she's dug into the ground with friction, right? Because if she slides back a little bit, it's like, well, you have to like subtract, you have to do some relative loss there. All right, that's not the question. I did say too, you could solve this before we got to this momentum stuff, but it'd be a more complicated process. Here's how you would have solved this back in the day, right? Remember, you're trying to figure out what is her speed going back for second base. Right? So, well, the velocity of the ball, it only got up to that speed because she threw it, it was accelerating for some time. So that speed, going back to kinematic days, was like acceleration times the time of throw, right? Acceleration times time, right? So if you were given that speed, now here's where you have to make a little bit of assumption, but that's okay, it ends up canceling out in the end. Let's say you come up with like a tiny fraction of a second of throwing. Then you could therefore calculate the acceleration. Then you say, well, what's the force on the ball? Less the mass of the ball times the acceleration. Here, guys, focus with me here. That's your math, right? So if you had solved that acceleration and given the mass of the ball, you could solve for the throwing force. Then you say Newton's third law of motion, the force on the ball equals the force back on her, equal and opposite, Newton's third law. Then you say force equals mass of her times her acceleration during the throw, where that force only lasts for a tiny fraction of a second. You have that right there. Her mass, you solve for her acceleration. Then we say her final velocity is what is the acceleration times the time of throw, which match that time. That's where even if you come up with a different time, I think it ends up canceling out the end. Right. And then you can get, okay, that's a long process, right? It involves a lot of little stuff, right? But the fast way we can do this is conservation of momentum. We're going to treat this as either like an explosion, like for the grenade, or like a reverse collision, different perspectives on the same thing. If you ran this film in reverse, it would look just like an inelastic collision. Guys, how much momentum in the system when she's just standing there at rest on the mound? Zero. Zero momentum. There's zero mass times velocity. There's only ever zero momentum in that entire system. Wait a minute, I thought the ball and she were moving. Don't they have momentum individually? Yeah, but it's going to be mass ball, velocity ball, plus mass pitcher, velocity pitcher, right? They're going opposite directions. And remember, velocity is a vector value. So these two are always going to zero out, right? So subtract one over. I could say mass pitcher, velocity pitcher equals negative mass ball, velocity ball. Right? As long as you know three of these, you can solve for, well, the fourth one in this case, velocity pitcher. Okay. So here, let's yeah, thank you. So I almost got this in terms of variables, so just go ahead and finish that. All right. We got mass ball, velocity ball over mass pitcher. Right. Then you can just plug in values. Let's say here, let's get some values going. I know right before I plug stuff in, let's make sure this makes sense. Right. The more mass of the ball for some given throwing speed, she would be thrown back faster, right? She like throws a bowling ball. Oh, right now, it's a lot of momentum the other way. Right? The faster she throws the ball, the faster she's moving back, right? The more massive she is, the slower she's moving back. That's an inverse relationship. Just plug in some values that could be reasonable. So mass of a baseball, I know is like this many kilograms, so I'll go ahead and use that. Okay. Let's say she throws it at 20 meters per second. Right? And let's say her mass is like this many kilograms. Right, kilogram. Right. Get some numbers here. Right. I'm looking at her velocity back for second base. Well, if towards home plate is positive, then her velocity is negative. And be this many, that'd be meters per second, right? Which is approximately 7 centimeters per second. There you go, about 7 centimeters per second. She's headed back towards second base would be a reasonable value. Right. Ignoring all the rotational stuff. Right. All right, I think that's a good pause point today. Pause point.